Hey, and welcome to this AVR training. This training will have 7 assignments that will be 7 different videos. The training will cover the analog signal conditioning peripheral, also known as op-amp, the new feature of the clock control, such as external high-frequency oscillator and clock failure detection, and the new multi-voltage I/O peripheral, allowing the AVR to operate on 2 different voltage domains. For all these assignments, the AVR128DB48 Curiosity Nano evaluation kit will be used. The kit includes a high-frequency oscillator and the possibility to power the AVR on 2 different power domains. The training manual, as well as all the code needed to complete this training, can be found in the links down below this video. Throughout this training, I'll be using the solution code to show what should be done and what needs to be configured. The first assignment will focus on the external high-frequency oscillator and clock failure detection. The objectives are configuring the Exoskf to be the main clock source, configuring the clock failure detection to generate a non-maskable interrupt when detecting a main clock failure. A non-maskable interrupt is an interrupt that will happen even if the CPU is already handling an interrupt or the global interrupt bit is not set. This means that a non-maskable interrupt will always happen straight away. We will also trigger a failure on the main clock. The AVR can test the clock failure detection by introducing an error on the clock through a software command. So let's have a look and see what we need to do in the project. So the first thing we need to do is initialize Exoskf. So we will set the crystal to be running in standby. This is so that the crystal will start up and we can verify that the crystal works properly before we switch over to the main clock. We will set the startup time to be 4000 cycles. We will set the frequency range to be 16 MHz. So we know that the high frequency crystal on the Curiosity Nano is a 16 MHz crystal. And we want to set the frequency range as low as possible, but still within the range of the crystal, because the higher the frequency range, the more power we will consume. Exoskf will be connected to a crystal and not to an external clock. And of course, we will enable the crystal. Then we will wait for the crystal to have started properly by checking the status bit for external crystal. After verifying that the crystal is working properly, we will switch the main clock source from the internal oscillator to the external oscillator. We will then wait for this transition to be over before we will turn off the run standby bit, because the oscillator is now in use by the CPU and we do not want the oscillator to be running if it is not needed. This is to save power. So these are all the steps needed to configure the external high frequency oscillator as the main clock source. Now let's go over to configuring the clock failure detection to be able to detect if the main clock fails. We will set which source the clock failure detection should be looking at, and this is of course the main clock, and we will also of course enable the clock failure detection. In addition, clock failure detection will create an interrupt, and we will set that interrupt to be a non-maskable interrupt. As we talked about, the reason you want to use a non-maskable interrupt is because that interrupt will always happen straight away. So if it's very critical for you to instantly react to a failure on the clock, then a non-maskable interrupt is the interrupt type you want to use. Down, if you look at the non-maskable interrupt vector handler, we will see that we first have to check what kind of interrupt caused the non-maskable interrupt, because there are several sources that can create non-maskable interrupts, but there's only one interrupt vector. We have to check what is the source of the interrupt. So that's why we check to see if you had a clock failure detection interrupt. And in the interrupt, we will simply just blink the LED on the Curiosity Nano. Another important factor of non-maskable interrupt is the fact that the only way to leave a non-maskable interrupt is with a reset. So you issue a software reset to restart the system. And what we will see by blinking this LED is that in the interrupt, we have a delay of 200 milliseconds, and we have exactly the same code in the main function. And the way that the delay function works is that it calculates how many CPU ticks it needs to create a delay of 200. And this calculation is based on the fCPU define. So here we have defined fCPU to be the external clock, which is 16 MHz, which means that this delay calculation will take 200 milliseconds. But when we go in the non-maskable interrupt, these calculations will still be based on if we were running at a 16 MHz clock, but because we got an error, the system will automatically switch back to the default clock, which is the internal 4 MHz clock. And therefore the calculations will be 4 times too slow, or there will be 4 times many ticks at what's needed to create 20 milliseconds, so it will instead be 800 milliseconds. And this way we can see that when the error happens, we will see that the blinking of the LED will slow down and it will be 4 times slower. The last thing we need to do is actually create the fault. So the system is set up that on a port B interrupt, which is the port that the button on the C Nano is connected to, we will of course clear the flag, as you should always do an interrupt. And then we will introduce the clock failure by setting the CFDTST bit. And this will introduce an error and should trigger the non-maskable interrupt. So let's flash the device so we can test this code. And now we can see the LED blinking. And if I press this button, we will see that the blinking slows down, which means that we have switched over to the internal 4 MHz clock. That's it for assignment 1. Thanks for watching.